Now we will discuss the Boolean function standard forms. We will check first what are the standard forms, the min terms and the max terms, the index representation of the min terms and the max terms. After this, we will move to the sum of min term representation, SOM, and the product of max term representation, POM. Then we will check how is this making complementing functions easy. After that, we will end up with conversion between the representations, and we will check a lot of examples during the subjects. The standard forms, it is useful to specify Boolean functions in a form that allow comparison for equality and has a correspondence to the truth table. The standard forms has two major types. The sum of min terms, SOM. For example, if you say f is equal to x bar y z bar or x y bar z bar. And here, f has three inputs, and the function contains two terms. Each one of these two terms has the three letters, whether in their original form or the inversion form. The other type is the product of max term. That's the other form, the other standard form, POM. For example, if we say J is equal to X or Y bar or Z ANDed with X bar or Y or Z. You can see again that G has three inputs, and in those two terms, each one of them has all of those inputs with the variable in its original form or its complement form. You can also see that when we what we mean by sum of min terms, those terms we call them min terms, and this is the sum of them. Similarly, in the product of max terms, those terms called the max terms, and we have a product between them, meaning we have an and. The sum means we have an or. So to define the min terms are and terms with every variable present in either its true or complemented form. Given that each binary variable may appear normal, for example, x, or its complement version, which is x bar. There are 2 to the power of n min terms if you have n variable. So, for example, if we have 3 inputs where n is equal to 3, then we have 8 different min terms. As another example, if we say that n is equal to 2, so we have 2 variables, x and y, this will be produce 2 to the power of 2, which is 4 different combinations or 4 different min terms. The first one being x, y, both of them are normal, xy bar, here y is complemented, x bar y, here x is complemented, and the last one is x bar y bar, and both of them are complemented here. So there are 4 min terms of 2 variables. On the other hand, the max terms are, we are ORing the terms instead of ANDing. So the max terms are OR terms with every variable present in either its true or complement form. The same thing, there are 2 to the power of n max terms if you have an n variable. And as an example, if you have 2 inputs, you will have those 4 max terms. Notice that the max term, now we are ORing either X or Y, X or Y bar, X bar or Y, X bar or Y bar. Those are the 4 different max terms if you have 2 variables, X and Y. To put them in a table, here, if you have 2 variables, X and Y, if we say that the first row index is 0, and the second is 1, and the third is 2, and the last one is 3, those are the index. So we have 4 rows, and we are indexing starting from 0 to 3. Now, the min terms for this one, you can see that it's X bar, Y bar. The second row, X bar, Y. The third row is X, Y bar, and the last one is XY. Those are the min terms. Now, the max term, you are actually looking it in the opposite way. So if you have a 0, it will be X or Y. Here, it will be X or Y bar because it's 1 here. The index number 2, you have X bar or Y, and the last one, you have X bar or Y bar. So the index above is important for describing which variable and the terms are true and which are complemented. Also, you should notice that if you know the min terms, you can easily find the max terms by applying De Morgan law. So if you have X bar, Y bar, for example, this is the min term. If you want to find the max term, you will apply De Morgan law. So you will break the line and change everything below. It will be X or Y. Now, we will give the min terms and the max terms for 3 variables. So now the index starts from 0 to 7. And for example, if we take this row, the min term will be X, Y bar, Z. That's the min term. And the max term will be X bar or Y. Now we are looking at in the opposite way. If it is 0, then it's Y or Z bar. Again, same thing as we said before. You can apply the De Morgan law if you have the min term to get the max terms. You can also notice that when you're finding the min term, it's actually a direct implementation of the truth table. So you can see that here you have Z bar, Z, Z bar, Z, Z bar, Z, and so on. Here you have Y bar, Y bar, Y, Y, Y bar, Y bar, Y, Y. And the last one you have X bar, X bar, X bar, X bar, X, 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 and X. Now you will check the standard order. The min term and the max terms are designated with a subscript. This subscript is a number corresponding to a binary pattern. And the bits in the pattern represent the complemented or normal state of each variable listed in the standard order. All variables will be present in a min term or a max term and will be listed in the same order. Usually this order is alphabetical. So to understand this, here are some examples. For variables A, B, C, if you want to check the max terms, you will start with A and then B and then C bar. For example, that's one max term. Another max term, A or B or C. You notice we are ordering now. It's a standard order. We always start with A or A bar, B, and then B or B bar, and then C or C bar. The min terms, here are 3 examples of min terms. Remember the max terms, there are or between the literals. In the midterms, there are and between the literals. Now, if you take those terms here, B or A or C, you see that you are not ordering here. You are misordering here. The order is not correct here, starting with the C. They are all not in a standard order. The terms A or C, you notice that you are missing B. B is not there. Here you are missing the A, here you are missing the C, or its complement. So they don't contain all the variables, and they are not max terms nor min terms. The purpose of the index. The index that we have for the min terms and the max terms expressed as a binary number is used to determine whether the variable is shown in a true or its complemented form. So actually, it's a short way of getting the min term just by knowing the index. Similar thing could be said for the max terms. So for the min terms, 1 means the variable is not complemented for the min terms. 0 means the variable is complemented. For the max terms, it's the opposite. 0 means that the variable is not complemented, and 1 means the variable is complemented. Here are some examples. Assume the variables are x, y, and z. The standard order is x and then y and then z. The index for 0, if it is decimal, it will be, because it's 3 variable, 0, 0, 0. So the min term will be x bar, y bar, z bar. And this is going to be m small 0. This is its index, m0, the index being 0. For the max term, remember, we are doing the opposite now. So it will be x, y, z. And there's or between them, x or y or z. And we will call this m capital 0. To show this in an organized way, check this table. Now, here we have the min terms. We have this table before, and we filled the min terms. Now we are adding the index, and you can see simply that those indexes starting from 0 to 7. Now we are saying that this one is m small 0. This is m1, m2, up to m7. You can also represent them in a matrix form. You'll notice that here we start from m0 to m7. And in the columns, we have from m0 to m7. Only in the diagonal, we have 1, which means that we have the correct min term, which is this one. This one being m0 means that you are choosing m0 and not m1, nor m2, nor m3 up to m7. They are all zeros. Similarly for the rest of the min terms. Now, the beauty about this, now, for example, if you want to find the min terms corresponding to m6, simply what you do, you say that I know the 6 decimal number is 011 in binary, which means the x is going to be not complemented, the y is not complemented, and there is a z bar. And this is the min term. Directly, you get it from only the index. You can check any of the other min terms. This is also applying for all of them. The max terms, you could do the same thing, but now you think in an opposite way. The 0 will give you the term, the normal literal, and the 1 will give you the term in its complemented form. So, for example, if we choose 6, the max term is x bar or y bar or z. And we order them in the same way the index from 0 to 7, we call them M capital 0 up to M capital 7. So, and again, now what happens if you do it in a matrix form, M0 to M7 here, and you do it again in the column, because the max terms work in an opposite way. Now, if you are choosing M0, you will make it 0 because you chose it. And the rest will be not choosing by applying 1. So you'll have a diagonal with zeros. Same thing for the max term. Or for example, you want to find M6. You would say that in binary form is 0, 1, 1. And now what you should do for the max term, you think in the opposite way. You would say, now we have 1 here, so we'll have X bar, or Y bar, or Z. And this will be M capital 6. Now, this is the same thing, but for 4 variables. If you have W, X, Y, and Z, the index will be from 0 up to 15. And you can check, I'll take one at random, for example, 11. So it will be, the min term will be W, X bar, Y, Z. W, X bar, Y, Z. And the max term, now we think opposite, W bar or X or Y bar or Z, which is W bar or X or Y bar or Z bar. And again, the index here is starting from M0 up to M15 in the min term. And for the max terms, start from M capital 0 up to M15. M capital 15. Now we will check the relationship between the min term and the max term. And you can notice up to this point, the min terms and the max terms, the product of min terms, or the product of min terms, or the sum of max terms, they are just an organized way of representing the Boolean equations. So we have the product of min terms, and we have the sum of max terms. Or it's the opposite way. The product, it's a product of the max terms, which means that you have a max term. For example, if you have 3 variables, X or Y or Z, and you have X or Y or Z bar, for example, you have a product between them. So this is a product of max term. This is a max term, this is the max term, and this is the product of the max terms. While here, you have the sum of min terms. So you have a min term, X, Y, Z. And for example, another min term, X bar, Y bar, Z bar. And you have OR between them. So it's a sum of min terms. So to find the relation between the min terms and max terms, we just do it. If you have the Morgan law, you know, it's break the line and change the sign. And it's 2 variations. If you have 2 variables, so M small 1, since you have 1, and you know 1 in binary is 1, 0, you have 2 variables. So it will be X bar Y. This is M1. M capital 1 would be X or Y bar. You can also notice that the min term M1 is equal to the complement of the max term M capital 1, and also vice versa. And this is what we said before. If you have any min terms, for example, let's say M7, This is the min term M7. If you want to find the relation between M small 7, the min term, and the max term M capital 7, so they will be equal to the complement of the other. Either you do it this way or you do it M7 is equal to M capital 7, and you put the bar here. It's either do it this way or that way. Both of them are correct. Since De Morgan theorem holds for an n variable, the above holds for any number of variables. Whether it's two variables, you have two variables, x and y, or three variables, x, y, and z, or four variables, and so on. Thus, in general, if you have m small I, it will be equal to the complement of m capital I. So the min term is the complement of the max term, or the max term is the complement of the min term. Let's see it for two variables. If you have 0, 0, 0, 1, 1, 0, if you have the truth table like this, x and y, the min term is x bar, y bar here, x bar, y, x, y bar, and x, y. And this is the matrix that we just mentioned. The max term will be this way. And you can see that the complement of this one is this one. You can apply it by, if you put a full bar here, and you break it, it will become x or y. Also, you can see it in the matrix form. If you have this one, this is the output being 1, 0, 0, 0. In the max term, it will be 0, 1, 1, 1. So each column in the max term function table is the complement of the column in the min term as well. So also this one will be the complement of this one. Here are the observations that we had. In the function table, each min term has one and only a single one present in the 2 to the n term. So you have a single one here. You have a single one here. You have a single one here for this row. And you have for this row a single one. For the max term, you have a single 0. And they are also in the diagonal. We can implement any function by, and this is one of the key results. We can implement any function, no matter what's the function, by ORing the min term related to one in the function table or within the truth table. And these are called the min terms of the function. Or you are ANDing the max terms, which is the zeros in the truth table. So if you look at the ones, you should find the min terms and OR them together. If you are look at zeros, then you should find the max terms and AND them together. There are two standard forms for stating any Boolean function. The sum of min terms. So you sum up the min terms or the product of max terms. Here are some examples. This table, we already discussed it before. The only addition here is we have a function called f1. It's 0, 1, 0, 0, 1, 0, 0, 1. If you want to find this function, you should look at the one, this one, this one, and this one. And you will find the min term corresponding to each one of them. So the min term here is x bar, y bar, z. Here it's x, y bar, z bar. And here is x, y, z. Or you could say that this one is min term 1, m1. This one is m term 4. And the last one is min term 7. Now you found the min terms, which is ANDing them together. Each min term, you have ANDing between the variables. you OR them together to find the sum of minterm. To find the sum of minterm. This is how you find a function using the minterm. If you want to find it using the same function, f1, but now you want to find it using max terms, you look at the zeros. And for each one of them, you find its max term, which is m capital 0, m capital 2, and so on. M3, M4, M5, and M6. And then you add those max terms together. Now this max term, for example, is x, y, and z. Remember, we are thinking opposite. For the last one here is x bar, y bar, z. X bar or y bar or z. So this is the first max term, the second, the third, the fourth, and the last one. This is m capital 0. This one is m capital 2. This one is m capital 3, m capital 5, and then m capital 6. So basically what we did, we looked at the zeros in the output function or the output column, and we found the max terms for each one of them. After we found those max terms, we AND them together. I should mention that usually we use the min terms more than the max terms, because in the min terms we look at the ones and we directly get it from here. If it is 0, then the x is bar, the y is bar, and the z is in its normal form. So that's why the min term is usually used more than the max terms. Now we will talk about the shorthand forms. It's a way of writing the function in a short way. So in the previous example, we have f1 is equal to m1 or m4 or m7. You could write it like this: the summation for the min terms, which is the small m, of 1, 4, and 7. If I write this down, you should know that those are the min terms. And from those min terms, you can get the function. For the product of max terms, in the previous example, we said m capital 0, m capital 2, and m capital 3, ANDed with m capital 5, ANDed with m capital 6. So we take the product of m capital of these indexes, 0, 2, 3, 5, and 6. Since we worked on this example, you can see if we have 3 variables. In this example, we had 3 variables. If we have 3 variables, then the indexes start from 0 to 7. If you have 3 indexes of min terms, then the rest will be on the max terms. So you can see that starting from 0, it's in the max term. If for example, in the min terms, 1, 4, and 7, the rest, which is 0, and 2, 3, 5, and 6 will be in the max terms, or the product of max terms. As an example, if we are asked to implement f2 in min term, and f2 has 5 variables, and you are given that this function is the sum of those min terms, 2, 9, 17, and 23. So you say, okay, I'll break it down: m small 2, m small 9, m small 17, and m small 23. M small 2, we'll write the binary form on the side so you don't forget. It's 0, 1. Since it's 5 variable, you will add 3 zeros. The 9 will be 1, 0, 0, 1, and 0. This is the binary of the 9, and the binary of 17 is 1. It's 16 plus 1, so it's 1, 0, 0, 0, and 1. And the 17 would be 1, 1, 1, 0, and 1. Since you got those indexes, now you can generate the midterm in literal forms. It's going to be V bar, W bar, X bar, Y, and Z bar. Or the second one is being M9, V bar, W, X bar, Y bar, and Z. M17, V, W bar, X bar, Y bar, and Z. And the last one is V, W bar, X, Y, and Z. And you OR them together. This will be the function f2, which is 5 variable. If you take this one as a max term, another example, it has 4 variable, f3. Those indexes are 3, M capital 3, M capital 8, M capital 11, and M capital 14. Again, you do the same thing. Now, the 3 is, since we have 4 variables, it's going to be 1, 1, 0, 0. The 8 is 0, 0, 0, 1. The 11 is 1, 1, 0, 1. And the 14 is 0, 1, 1, 1. Now think the opposite way, because this is a max term. So it's going to be W, X, Y bar, Z bar. That's the first max term. And you OR them together. You OR them together. So you have W or X or Y bar or Z bar. Here you will have W bar or X or Y or Z. And here you will have W bar or X or Y bar or Z bar. And the last one will be W bar or X bar or Y bar or Z. Once you find the max terms, you sum them together. So this is the sum of max terms. This is the implementation using the standard forms, whether they are min terms or max terms. Now we will check more examples, more terminologies to understand this better. So the standard sum of min terms, any Boolean function can be expressed as a sum of min terms, SOM. For the function table, the min terms used are the terms corresponding to the ones. For the expansion or for the expression, you expand all the terms first to explicitly list all the min terms. And then you add any term missing a variable V with V or V bar if you are having something missing. To understand this better, if you have this function, f is equal to x or x bar, y bar, we know that it has 2 variables. This is a min term, but this one is not a min term. To make it or to force it to be sum of min terms, you have to convert this to a min term as well. So we know it's missing a y. Since it's missing the y, we add it like this, y or y bar. We are using the Boolean algebra. After that, you distribute the x here and here. It will be xy or xy bar or x bar y bar. And now you know that there are 3 min terms in this function. The first one being, this one would be m0, m small 0, and this one will be m small 3, and this one will be m small 2. Or you could write it this way, the summation of the m small 0, 2, and 3. This is the sum of min terms. Similarly, you can do this for the max terms. This is another example for as a sum of min terms. Let's say you want to convert from the sum of products. The sum of products, something like this. This is a product. And this is a single value. a single variable, we could assume that it's a product. So there are products, it's not min terms. And you sum them together. How to make them sum of min terms? How to convert from SOP to SOM? You do it by checking how many variables first. There are 3 variables, A, B, and C. You can see it in the function. And you know that you are missing the B and C in this term, and you are missing the A in this one. So you add them this way, A, and then you add it with B or B bar, and this one you add it with C or C bar. Here you are missing the A, so you add it this way, A or A bar, and add it with B bar, C. And then you do the distribution. The distribution here is, you know that it will generate 4 different terms, this, and that. You can do it by applying it like this, A and B and C. So you take this, and that, and then you take A, B, and C bar, and then you will take A, B bar with C, and then A, B bar with C bar. Similarly, do it here. This is easier. A, and it with B bar C, A bar, and it with B bar, and it with C. I should also mention that here we used prime. This is not, I mean, this is okay. We could use the prime or the bar. In this class, we usually use the bar. Honestly, I just miss it here. It should be bar. Using a prime or a bar doesn't make a difference. Now, after that, if you have repetition, you cross one of them. You can find there is a repetition between this one and this one. There is a repetition here, so we cross one of them. So originally they were 1, 2, 3, 4, 5, 6, and now they are 1, 2, 3, 4, and 5. We crossed one of them. And now we know which one corresponding to which midterm. This is M7, this is M6, this is M5, this one is M4, and this is M1. To understand how did we do that, because you get the binary first. You get will be 0, and this one 0, and this one is 1, and you know this is 4, M4. And so on for the rest. After that, we just order them and we write them in the shorthand form, which is 1, 4, 5, 6, and 7. We do the summation for those midterms. Now, what about the max terms? We'll do the same thing for the max terms. Any Boolean function can be expressed as a product of max terms, which is corresponding to zeros in the truth table. What you do, you expand all the term first, to explicitly list all the max terms. By applying the distributive law first, you do the distributive first, and then after that, you or any term missing with a variable, for example, V with V and it with V bar. You compare this with the slide before, you will see the difference. As an example, if you take the same example that we had before, and now we want to generate the product of max terms. To do that, you do the distribution. And remember, you could distribute the or to the and. You could say x or x bar, and it with x or y bar. X or x bar, and it with x or y bar. So that's what you do first. And you can notice if you do that, x or x bar is actually 1. So you can take it out and you end up with only x or y bar. You can notice here that we have, so far, only the x and y. And we know that there are 3 variables. So we are still missing the z. To do that, you add it this way. You add it like or, and then z, and it with z bar. If you add add this part z or z bar, I mean z ANDed with z bar, you are not changing the function. You are not changing the function. And then you do the distribution as we described, like this: x, y bar, z, x or y bar or z, and then x or y bar or z bar. This way you did the distribution, your distribution, the AND to the oops. And this way we know that we have two max terms, M2, M capital 2 or M capital 3. How did we find it? Remember, we are doing it the opposite way. So this will be 0, and this will be 1, and this will be 0. This will be 1, 1, and 0. So this is 3. This here is 3. And here it's 2. So M capital 2 or M capital 3, and you do the product of the max term this way. That's another example. If you want to convert from sum of product, you can see these are products. They are not max terms. So how to convert from sum of products to product of max terms? You notice here that you have, again, 3 variables, and you do it by using Boolean algebra. You can see at the beginning we are using this technique, which is the distribution of the x this way, x or y, x or z bar. We did it here by distributing this term to the others this way, a bar with the other midterms. So that's the first one, and the second one with the b, like this, the b bar with the first. So first a c bar or b c or a bar, and the second is a c bar or b c or b bar. Now, remember, we have the simplification rule. If you have it this way, you could cross the x bar and you end up with x or y. By doing the simplification, you can see that you have here this with that one, a c bar with a bar, and you can cross the a. Similarly here, you have this with b bar, and you can cross the b. So we apply the simplification, and you are getting closer to the product of max term. You are getting closer to generate a max term here and a max term also here. Now, on this step, we are using, again, the simplification by looking at this with this one. So we can cross the C. We generate only the B. And between those and that, this and that, we can cross the C bar and we generate this one. And from this, you only need to reorder, starting with A bar or B or C bar, A or B bar or C, to generate the two max terms, this being max term of 5 and this is max term of 2, or you can write it like this: product of max term 2, 5. So to summarize this, you do the distribution and then you apply simplification. Sometimes you apply it more than one time. The function complements. We mentioned before that the complement of a minterm is its corresponding max term, and vice versa. Now, what about functions? So we are looking for the function complement. The complement of a function expressed as sum of minterm is constructed by selecting the minterms missing in the SOM standard form. And the complement of a function expressed as a product of max terms is constructed by selecting the max term missing in the POM standard form. Alternatively, the complement of a function expressed as SOM is going to be simply the POM with the same indexes. As an example, let's see this. If we consider this F, 3 variables, X, Y, and Z, and you have those minterms. So this is a sum of minterms. To get the complement of F, either you use the same sum of minterms and you fill in the indexes that are not presented in the original function. So the indexes that were not presented, they are 0, 2, 4, and 6. That's one way to find the complement. Or the other way, the second way, is you use the same indexes, but instead of the sum of minterms, it will be the product of max terms. That's how you generate the function complement. To explain this to you, we will show you another way, and we will give you more examples. To convert from the sum SOM to POM or vice versa, we follow these steps. Find the function complement by swapping terms in the list with the terms that are not in the list, and then change to POM or vice versa. So if you are giving this function, for example, this is how you convert between forms. You want to get to move from the sum of minterms, and you end up with the product of max terms. One way to do it is generate or get the complement, which is by having sum of minterms, but listing the indexes that were not presented here. And after that, you get, this is now the complement of F. You get the equivalent of this complement by using the product of max term. And to get this equivalent, you change the sum to product and change the indexes. 0, 2, 4, 6. It will be 1, 3, 5, and 7. And after that, you get the F from here by keeping the product of max terms and changing the indexes to the indexes that are not presented here. You could also say that this and this are equal. So you can see this is the sum of minterms, and this is the product of max terms. Here are the 1, 3, 5, and 7. Here you have 0, 2, 4, 6, which is the indexes that are not listed. Similarly, here, they are equal. This is the sum of minterm. This is the product of max terms. If you are listing indexes here, the indexes here will be the one that are not listed. Now, conversion between minterms and max terms. If you have this function, the same function that we are listing, if we have the summation of 1, 3, 5, and 7, we expand it this way. This is the minterms, or the product of, or the sum of minterms, and we get the complement by getting this the sum of the minterms of the indexes that are not listed, which are those minterms. Now we have the sum of minterms for the function and for its complement. So also for the equivalent of the complement function, we get the product of max terms with the indexes that are not listed here, and they will be listed, as you can see here, as product of max terms. After that, you will complement it again to generate the original function, which is the product of max terms with the indexes that are not listed here, and it will generate those max terms for you. And you can clearly see that this one is equal to this one, which is what we said here, which means that this is actually equal to this one. And here's the beauty about it. We can easily get this by changing the summation to product, min terms to max terms, with the indexes, if they are here, 1, 3, 5, and 7, there will be the one that are not listed, which is 0, 2, 4, and 6. Don't forget, we have 3 variables. So all the indexes that we have is from 0 to 7. Now, to prove this to you in another way, you can get this one here and then apply the De Morgan law. You break the line and change the sign of everything below, and you will get from X bar, Y bar, Z bar, you will get X or Y or Z, and so on. And you will find that they are, it is correct. This part here is actually equal to this part. You can say similar thing between this one and this one. You can alternatively use the truth table. And we mentioned this before somehow, and now you will see the full picture. In the truth table of a function, for example, f1, the SOM of f are the terms corresponding to the ones. This is the sum of minterms. Now, if you generate those sum of minterms, the other sum of minterms that are not presented in f, it will be f bar. If you want to do it as a product of max term of a function f, they are the terms corresponding to the zeros in the truth table. And any max term that are not in f, it will be presented in f bar. To see this, let's start with the ones in the truth table and get the minterms. You know that we have 4 ones here. We get the minterms, which are 1, 3, 5, and 7. 1, 3, 5, and 7. Now, this is for the function f. For the f bar, it will be the product of max term of the ones that, or the indexes, the same indexes that you have for the function. And it's here represented to you in the red arrows. And this makes it easier for you to remember. Now, if you have f and you get it from the 1, as we said, 1, 3, 5, 7, you have the same indexes, but you change from the sum of min terms to product of max terms to generate f bar. Now, let's look at the other way of doing it. The other way of doing it is look at the zeros and generate the max terms. So you have max term 0, max term 2, max term 4, and max term 6. The function will be the product of max terms 0, 2, 4, 6. To get f bar, you keep the same indexes, but you change the product of max terms to sum of min terms. Usually what we do in the design, we do it like what we did in the red arrows, using minterms. And once you find the minterms, you can generate the F bar using a product of max terms. For example, for this function, you only want minterm and minterms only. Then you take this one for F, and you can take this one for F bar. If you want max terms and max terms only, then you can take this one for F as a product of max terms, and you take this one as F bar product of max terms. I hope after this is clear for you. Now, just to make sure you understand everything so far, the standard sum of product, SOP form, they are equations that are written as an OR of AND terms. The standard product of sum, POS form, they are equations that are written as an AND of OR terms. So now we have sum of product, SOP, and product of sums, POS. They are not necessarily max terms or min terms. As an example of SOP, you can see here A, B, C, or B, C bar, or C, or A bar, B, or A ended with B bar, ended with C bar, or A bar, B bar, C. So they are ANDs or together. This is the sum of products. We have products and they are summed together. The product of sum, you have a sum, another sum, and a single value, we'll consider it a sum too. And then you have a product between them. This is the product of sum. Other cases, like those ones, or these ones, these are mixed form. They are neither sum of product nor product of sum. So here you can see this is a product, this is a product, but here we have a sum that is ANDed with the letter. So this doesn't make it a sum product nor a product of sum. Similarly here, because we have this one here. Now to convert from a non-sum of product expression to sum of product expression, you simply expand. So if you have this function, F, A, B, or C, ORed with D or E, to get the sum of product, you do the expansion, the C, you distribute it into both variables. It will be AB or CD or CE, and we are done. This is the sum of product. Now, to do the product of sum, you do distribution. So you distribute the A here and also the B here, and you keep doing this. So if you do it, it will be A or with this term, B or with this term, and you AND them together because there was an AND here, it will be this AND. After that, you can see this one here. Your goal is to get product of sum, something like this. So you should do that again. The distribution, you distribute the A here and also to this one. So it will be A or C and with A or D or E. A or D or E. This AND is the result of this AND here, this one. You do the same one here, the same thing. B, you distribute it with the C and with this one here. So it will be B or C and it will B or D or E. And now you just order if you need to. This one will be A or B. This one will be A or D or E, and this one be B or C. So you're just listing them. You don't need to reorder anything. And this is a product of some. The decision to use two-level or multiple level implementation is actually complex. You can see here that, for example, should we design this or this one? If you design this one, it will be like this. It's two-level, and then you OR them together. If you use this one, it will be like this. You get the A ANDed with the B. We're done with this. And then you'll do the other entity, which is D or E. You get the D or E first, and then you AND them with C. You get the C, and you AND it with them, and you get it here. And then you do the OR between those two here. So should you use this design or this design? The choice sometimes it's complex. It's not clear for you which one to use because there are different gates, different number of inputs, different delay. Here you have only two levels. Now here you have multiple levels, 1, 2, and then 3. So probably the delay here is longer. But as a cost, you have here 2 inputs and 2 input and 2 input and. Here you have only 2 ANDs with 2 inputs. You have a single OR, but it's 3 input here. You have here 2 OR, and each one of them is 2 inputs. So there are multiple factors of choosing between which design you should adopt. The standard sum of product, the SOP, is actually a sum. This is the formal definition of it. The sum of terms form for n variable that can be written down directly from a truth table. The implementation of this form is two-level network of gates. If you have sum of product like this one here, you will design it this way, and it will be definitely two-level. The first level is ANDs, and the last level is OR. So the first level consists of an N input AND gates, and the second level is a single OR gate, but with multiple inputs that are fewer than 2 to the power of n. This form often can be simplified so that the corresponding circuit is simpler. So we will find in the optimization in another video that you can simplify functions that are represented using only minterms in another way. To understand this better, let's see that we have this function, FA function with 3 variables, A, B, and C, and it has those minterms, 1, 4, 5, 6, and 7. Those minterms are the one that are listed here. And this function now is in the sum of minterms form. To do this function, or have this function as a block diagram, it will be like this. You can see it has 2 levels. The first level is ANDs. Each one of them has 3 inputs because you have A, B, and C. And after that, you have in the second level a single OR gate with 5 inputs because you have 5 different minterms. The equivalent of this function is actually this symbol, 2 gates, only 1 AND and 1 OR. To get this one, you can apply Boolean algebra like this one. So you can see that what we did here is we found out there is a common factor for all of them here, and we get the A as a common factor. and we got the rest here. And you can see that from here, we have a common factor between those two, which is b bar. And we have a common factor between those two, which is b. And we can rewrite it this way. And after this manipulation or Boolean algebra, you can cross this one and cross this one, become only one. And this will be a bar, b bar, c, or a. And you can say that, okay, we have one entity here, and we have a and a bar, and we know by applying the simplification rule that we can cross this one. It will be b bar, c, or a. We reorder like this, and we can write or draw the block diagram this way. You can compare those two. The first one has 15 literal or literals. Here we have only 3 literals. Now here is the key question. Is there another way other than applying the Boolean algebra to get this simple block diagram from a min-term form, which is the standard form, a sum of min-term? And the answer is yes. And we actually can use what we call K maps. We will see this in the next video.